Hi everyone. My name is Shihab Khanur, and we are both researchers from University of Malaysia, Perlis, SEG University, and University of Wisdom. And the title of our paper is Generation of Multimode Orbital Angular Momentum Waves Using Wearable Antenna. Well, this is the outline for my presentation today. Well, every generation of technology basically refers to 10 years. So the fundamental objective to deploy new generation of technology is basically to improve the data rate, to provide wider bandwidth, and to allow new platform to implement new applications for our daily lives. And for 5G, well, 5G is basically focusing on higher data rate, low latency, massive connectivity, so that new applications such as virtual reality, augmented reality, autonomous vehicles, and so on can be implemented in a larger scale. Well, it can be seen that the demand for data consumption is increasing exponentially. And on an average, it can be seen that a person has around 3 to 4 devices connected to the wireless network. And at the same time, if you look at this graph, it can be seen that on an average, a person consumes around 9.1 GB of data per month. And this demand is increasing exponentially, and it will be increasing in the upcoming days as well. As far as the Shannon's theorem, it is expected that based on the current infrastructure that we have, by the end of 2030, we will reach the maximum upper limit of the facility that we have now. Hence, we have to find an alternative way. So there are multiple ways to increase the channel capacity, such as this special multiplexer, the transmission bandwidth, and the modulation order. Well, modulation order and the transmission bandwidth are not going to be effective for the upcoming generation of technology. Hence, the only option we are left with is the special multiplexing order. So in special multiplexing order, basically that main data, it splits into multiple data packets, and these data packets are being sent separately. And when we talk about the special multiplexing order, that's where the idea of orbital angular momentum waves, OM waves, comes in. So what makes OM waves separate than the other electromagnetic waves, such as the linearly polarized wave or circularly polarized waves? Well, in OM, we have a phase factor. So this is the phase factor which is not present in the linearly polarized waves or the circularly polarized waves. Because of this phase factor, the wavefront of these OM waves tend to be helical in shape, and the phase distribution, it's tend to be spiral in shape. Because of this helical wavefront, so we can implement different modes of OM waves, and these modes are orthogonal to one another. So we can assign different signals to different modes, and these modes can be transmitted at the same time using the same frequency without interfering with one another. As a result, we can increase the channel capacity, and the spectrum will be more efficient. And yes, these are the major advantages of using OM waves, where we can increase the spectrum efficiency, as well as we can actually transmit more data using the same channel, and it will eventually increase the channel capacity. Now, talking about the wearable communication, well, in 21st century, the demand for compact, flexible devices are increasing. And when we talk about the flexible electronics, well, wearable antenna is very high in demand because of the advantages such as it's inexpensive, it's lightweight, thin, comfortable, and it is robust. So for our research, we focused on generating multiple OM modes using flexible textile antenna, and the substrate that we used was felt. And the overall antenna dimension was 156.5 mm by 170 mm, and we used the concept of microstrip patch antenna. So in OM waves, to generate mode one, the phase difference between the patches should be 90-degree. And from this study, we can see that yes, for patch 1 to patch 2, the difference is close to 90-degree, and the difference between patch 2 and patch 3 is also close to 90-degree, and the difference between patch 3 to patch 4 is also close to 90-degree. So this 90-degree phase difference is required among the adjacent patches or radiating elements to generate mode 1. So for our design, we are focusing on generating mode +1 and mode -1. These two modes have the same number of 1, but they have different signs. It means one will be one mode will be in the clockwise direction, and the other mode will be in the anti-clockwise direction. And we use the concept of pin diodes to control the feed line and to activate the patches. And we use 16 pin diodes to block the current. So by blocking and allowing the current, we can actually activate either mode +1 or mode -1 using the same antenna structure. Talking about the S11, well, we were focusing at 3.5 gigahertz of 5G, and then it can be seen that yes, our antenna, it worked at 3.5 gigahertz, and at 3.5 gigahertz, the reflection coefficient was negative 17.305. Plus, the bandwidth coverage was around 700 megahertz, which was from 2.95 gigahertz to 3.65 gigahertz. And 3.5, it falls within this range. And for both +1 and -1, well, they achieved almost the same bandwidth. Talking about phase distribution and intensity distribution, well, one of the feature of OAM waves is the spiral phase distribution. So for +1 mode, we can see, yes, it's a clockwise phase distribution. And for -1 OAM mode, the phase distribution is anti-clockwise. And another feature of OAM waves is the intensity distribution, where there should be a null or dark spot in the center. Yes, for both +1, -1 mode, we can see there is a dark spot in the center. The third parameter to confirm the generation of OM waves is the null in the center. As you can see here, at 0 degree, there is a null. For OM +1 and for OM -1, there is a null at 0 degree as well. And this 0 degree is basically the bore side direction. So this is one of the features to confirm the generation of OM waves. And talking about the mode purity, so yes, among all other modes, mode 1, it achieved 47.78, which is the significant part of the overall mode generation. Since we were focusing at mode +1, hence it can be seen, yes, the mode purity is higher for mode +1. And when we generated mode -1, it can be seen, yes, compared to the other modes, the purity of the generated mode is 47.91. And it can be seen for both mode +1 and mode -1, the purity is almost close. And since we are focusing on the wearable antenna, hence the specific absorption rate is very important to make sure that, yes, our design is safe for human body. So it can be seen that the SAR value that we achieved for 1 gram of tissue was 0.00946 watt per kilogram, and for 10 gram of tissue was 0.00467 watt per kilogram. And both these values are within the acceptable range. And compared to the other previous works, it can be seen that yes, our proposed design, it achieved relatively better, more purity, and we used less number of pin diodes, and our design was mainly focusing for the 3.5 gigahertz band of the 5G spectrum. And to conclude that, yes, to the best of our knowledge, this is the first paper where actually we used the flexible substrate to generate mode +1 and -1. In other words, we generated two different modes of OM waves, and this design can be scaled up to generate multiple OM modes for the upcoming future generation of communication system. And the future work can be focusing more on to increase the purity of the OA modes to make sure the modes are more orthogonal and separate from one another, and also to make sure the antenna is more compact in size. These are the references that help us to carry out our research work. And having said that, thank you so much.